All right, so let's get started. This is lecture 9, and we are going to continue our coverage of rigid body equilibrium problems in 2D. And for the time being, we are going to focus on case 1. That is finding only the external reaction forces. We should start charging some penalty fee for those who show up late. Okay. All right. Okay, so I'm going to do a few examples. Okay. I will start with this problem first. Let's say you have a frame structure that looks like this. Okay. It is supposed to support these two external loads that act on this side. These two loads are applied at equal distances here. This is 0.4 meter, 0.4 meter. The structure is supported this way externally. At point C, there is a pin that is holding it in place. And then this point B is attached to a cable, and this cable is connected to someplace, point A, on the ground. And this distance is given. This is 0.18, and this distance from support C is 0.24 meters. So this is our structure, and we want to find what are the external, so find forces at C and B, the two locations that the structure is supported externally, or find external reaction forces, find support reactions at B and C. They're all the same. So what are the steps that we should follow? Step 1, set up an X, Y coordinate system. Step 2, cut the structure from all its supports, only put back the externally applied loads, and in place of those two supports, replace them with the forces that they represent. At point C, we have a pin. So we have two unknown reaction forces here. At point B, we have a cable attached to the structure. So cable obviously goes, it represents one force along the direction that the cable is attached. And by the way, the slope here is given because this is 0.18.24. So if you summarize that, you get this to be 3, 4, 5 slope. So this is the problem, free body diagram. So this is 75% or 80% of the solution process. With that set up, then we start with summation of moment equal to 0 as our first equation of equilibrium. Taking the summation of moments about the point of intersection of two unknowns. Where do you suggest that I should take the summation of moments? Any idea? Anybody?
Point C, potentially?
Point C is a good one because you get rid of these two. But it happens that in this problem, You could also do this. If you continue this, or the point A where this cable was originally attached, CX is along this line. So this can be also a point of intersection of two unknowns, those two unknowns being this one and this one. So that's another option. So you can take either uh, A or C. I will consider C, and therefore, as always, when you have an inclined force, resolve it into its components. This would be, given the slope, this is 4/5 of t. This would be 3/5 of t. Okay? So I will take summation of moments then, but c is equal to 0. So what do I have here? This force goes through point C, so only this component generates a moment about C, and it is in the opposite direction, I mean in the counterclockwise direction. This is the vertical distance from here to the line of action of that force. So you have 4/5 of T times 0.18. These two don't generate moment about point C. We have these two, both of them generate moment clockwise. This one would be then 240 times this distance, zero point 0.4 negative, and this one also generates a negative moment. This distance is 0.8 is equal to 0. So from here, you find T, that comes out to be 2000 Newton. Any question? If you had taken this as the point of intersection of two unknowns, right, you would find CY first, but I didn't do that. So that was the first equation of equilibrium, right? So now I write summation of forces along X equal to 0. What do I have here? I have CX minus 4/5 of T, 2000, and that's it. So this is equal to 0. That gives me Cx of 1600 Newton. If I use now summation of forces along y, the last equation of equilibrium, I have Cy minus this force, which is 3/5 of 2000 minus 240 minus 240 equal to 0. Okay, this is 1200, this is 480. I get this comes out to be 1680 Newton. Okay, so this is upward, this is acting in this direction. Any questions? Yeah, in the other section, I used point A to find the answers, and I found CY first. Okay, so if you used summation of moments about A equal to 0 as the starting point, that would give you CY first.
Could you explain your moment equation one more time?
Sure. Moment equation, I'm taking summation of moments about the point of intersection of two unknowns, right? Of course, I've resolved this force into its components. You can resolve it either at this point or this point, doesn't matter. It's easier here. So, what are the forces that generate moment about point C? This one, what is the vertical distance from here to here? 0.4. This one, vertical distance is zero point 0.8. How about these two forces? This one goes through C, so doesn't generate a moment. Is only this component that generates moment about C, and the moment would be counterclockwise. Think of that linkage, what direction it rotates when the force moves in this direction. And what is the distance? Is given 0.18 times the force, which is 4/5 of t. And that gives me the moment equation, and I find t. Does it explain? Does it,
Yeah, thank you.
great, thank you. Okay, any other questions? If not,
So if you were to use point A instead of point C,
mhm.
would the horizontal component of T, forfeits T, generate a moment about A?
Oh, if I use this,
Yes.
oh, if I used A, what I would do, I would leave T as is. I won't resolve it into the two components. So I can see that T is going through A and CX go through A. So I would only have CY as the unknown. You see what I mean?
Right. Okay.
In other words, if I use this, this is what I would use as my free body diagram. So these two forces would go through A and cancel out. So I end up with only this one. Okay. All right. Good question. All right. And let's do another problem. So another problem I want to do is this. This is actually from your book 429. You have a bracket or some kind of a structure like this. It is supported at this point, which is 3 inches from the top, and this length is 12 inches long. This bracket is designed to support this applied load of 90 pounds. So it's obviously with only this supported on a stable. So what we do, I would connect point E. Let's see, this is C, this is A. Going all the way here, going around a pulley, and then come here, connect to point A. So this cable is also acting as a support to keep this in equilibrium. All these dimensions are given. This is given as 7 inches. This distance is given as 5 inches. And obviously you can see from here, this is 12 inches. Okay, so again, we want to find forces at support D and in the cable. These are what mechanisms that are supporting this structure. So step one again, set up an XY coordinate system. Step two, I would separate this, detach it from what is supporting it. So at this point, you have a pin. So you have represents two unknowns. At this point, you have this cable. So you have this force T going in this direction. And at this point, you also have this force T along this cable. And the slope of this cable would be what? 12, 5. So this becomes 13. Okay. All right. So this is, I would resolve this into its components. That is, I would resolve this into these two components. So this is 12, 5, 13. So this component would be 12 over 13t. This component would be 5 over 13t. and I get rid of the original force. So this is the free body diagram. And of course, I have this 90-pound force applied. So this is the free body diagram, 75% of the problem. Any questions on that one? No? So once you set that up, the next step is summation of moments about the point of intersection of two unknowns. I will take summation of moment about point D. Okay. You may say that, okay, why don't I take summation of moments about here? Because you have this unknown and this unknown. If I take summation of moments about point E, although there are two unknowns, however, the way the geometry is set up, you end up with two unknowns still in that moment equation, dx and these two here. So this is the best point to choose. Okay. So with that said, let's do that. Summation of moments, you have this 90-pound generating a moment, positive moment about D. This distance is 9. So you have 90 times 9. This one generates also a positive moment about point D. So we have T times that distance is 3 inches. Then you have the moment of this force. This is the vertical distance. So you have negative 12 over 13 T times this distance given 7. And this one, the vertical distance is this. So you have negative 5 over 13T times this distance, which is 9, equal to 0. And that will give you, if you solve that, you get T comes out to be 117.4 pounds. And came out to be positive. That means the assumed direction for T is correct. Any questions? If not, let's go with the second equation of equilibrium, summation of forces along X. So you have 5 over 13, this force. You have 90-pound force. You have dx, and you have this force, okay, T, which is 117.4 equal to 0. So if you solve that equation, you see dx comes out to be positive 72.5 pounds. And the end result is positive. That means the assumed direction is correct. Now, the last equation, summation of forces along y. So you have 12 over 13 times 117.4, this force. You have dy, you assume that in that direction, equal to 0. And you see that this results in a negative value of 108.4 for dy. This negative value indicates the assumed direction you have selected for dy is wrong. So you have to correct that. Once you correct that, this becomes positive because this was supposed to be negative. So this is the answer. Any questions? I'm going to pause a little bit just in case you're writing things down and gives you more time if you have any questions to ask. No?
Can we leave dy negative?
I'm sorry?
As the final answer, can we leave dy negative?
No, no. Because the value, the magnitude is always a positive value. And not only that, if you leave it as negative, that means your free body diagram is not right. Because that force on the free body diagram actually has to act this way. So that's what my strong suggestion. Any other questions? If not, let's do another problem. Okay. Okay. We have a frame that looks like this. Is a strange looking, sorry about that, structure. So this structure is supported by a roller here or a slot that allows motion up and down. Another roller here that allows motion this way and that way, and yet another roller here that also allows motion in these directions. Let's see. This structure is subjected to these forces. An applied load of 20 Newton here at point B. Let me call this A, B, C, D, label them. Another load applied here, 40 Newton. And you also have a moment acting on this structure, a 20 Newton meter. These dimensions are given, 2 meters, 2 meters. These dimensions are given. This is 3 meters, 3 meters, and this direct dimension is given as 2 meters. So the problem is asking you to find forces or reaction, external forces at A, B, and D, where you have these supports. Any questions? All right, step one, set up X and Y coordinates. Step two, draw the free body diagram. Okay, to save time, I'm just going to redo the free body diagram on this by removing these supports. This support represents a force that is perpendicular to the direction of motion here. This is the motion. This is the motion. So RA would be this way. This is the motion. RB would be in this direction. So you have 1, 2, 3 unknowns. Okay. As I said, we always start with summation of moments about the point of intersection of two unknowns. So where would be a good point of intersection to consider? Any ideas?
Could you use point C, even though there's not any like forces
Yes,
on that point?
that's a very good point. Because if you continue this, you continue this, they intersect at that point. Do you see another possibility maybe? How about if I continue this and continue this? Unknown. They intersect at a point which is outside the structure, which is okay. So you can take summation moments about either C or summation of moments about point H is equal to 0.
If you used point C, would you have to, like, wouldn't the moment at point C be 20 because you have a moment there, or would you
Yes,
just ignore that for the
yes.
20?
That 20 moment is a moment. So no matter where you take summation of moments, this is a free moment, is a couple. So that adds to the equation of moment.
Okay.
It could be a good question. Yes. Any other questions? No?
Professor, do you mind pulling the paper up just a little bit? There's something that's kind of cut off at the top.
Oh, the top, here we go.
Thank you.
Better? Okay, great. Any other questions? All right. So I have these two choices. I will take this one. You know why? The reason I take that one, because not only you would eliminate the moment of these two forces or getting rid of these two unknowns, you also don't have to worry about the moment that this force generates because that goes through that point. So you only end up with with this unknown and the moment of this force and this existing moment. So that's what I do. You can take summation of moment about C. That's fine. You get rid of these two unknowns in that case, you end up with this unknown. Either one is fine. So I will take summation of moments about H is equal to 0. So what do I have? I have the moment of this force. This is the vertical distance between this force and that point. So, and this is going counterclockwise. So you have RA times 2. These two don't generate any moment about H. This one doesn't. You have this one, which is clockwise. So negative 40 times this vertical distance, which is 2 and 2, 4. And then you have this applied moment, which is 20 Newton meter, is equal to 0. So if you solve this, you get RA comes out to be 90 Newton meter in this assumed direction. Came out to be positive. That means this direction is correct. All right. So that's the first equation. Second equation, I take summation of forces along x is equal to 0. You see that in this problem, because of the specific and unique configurations that these forces have, if you write this equation, you see you have only one unknown, that is RD, no other forces in the x direction, that goes to 0. So you're going to tell me, or why didn't you start with that equation first? You could have, but only in this particular problem. The reason I always start with summation of moment, because in general, that is the equation that gives you only one unknown and one equation. But there are special cases like this, and nevertheless. So the last equation of equilibrium, summation of forces along y. What do you have? You have RA positive. You have RB, you've assumed to be positive. You have negative 20 Newton, and then you have negative 40 Newton force equal to 0. And if you solve this, you see that this was RB was 90. So you see that I'm sorry, RA was 90. And you see that for RB, you end up with negative 30 Newton. That means this force is downward. So the assumed direction here was wrong. So I will go there and make a correction to my free body diagram. That means this should be negative. This becomes positive, and that's the direction that this force is acting. Okay? Any question? No question? All right. Okay, so let's do another problem. We have time, so we'll take advantage of that. I'm going to do problem 422, which is a good problem, is in your book. You have a frame with these given dimensions. You have an applied load. This frame is designed to hold this force of load of 75 applied in the middle of this top portion. The frame is, and this side is 12 inches long. Frame is supported at this point A by a pin, and at this end B, we have a wheel that is sitting on an inclined surface. that makes an angle of 30 degrees. Oh, by the way, I forgot actually, because this was a good question somebody asked in the other section. Although you didn't ask that question, but it may be a good idea to go over that. The individual asks, how in the world, if this is a roller and you say motion can take in this place, in this direction, then in that direction, but what you're showing me is something like this. So that means this roller can be lifted. This is just a symbol. What this means in this case, for instance, is you have, say at point B, you have a mechanism like this. So this is what that support B would be. So you cannot move it in this direction. Motion is only allowed in this direction. But anyway, I thought that was a good question someone asked in the previous section. Okay, let's get back to this problem. So we have this frame loaded like this. And again, we want to find external supports or forces at A and B. Okay, so again, set up your usual X and Y coordinate. Step 2, draw the free body diagram. How does free body diagram look like? You have this is the frame. At this end, it's clear that point A, two unknowns, probably in these two directions. Here, you have a roller residing along this surface. So an unknown force, this represents an unknown force that is acting perpendicular to the potential direction of motion. Okay, so this angle was given 30 degrees. So this would be 60 and this would be 30, although my drawing does not do justice. These more look like this equal angles, but anyway. So we have that unknown RB there. I would resolve that into its components along these two directions. That's the first thing I do. So this would be RB cosine 30, which is the square root 3 over 2. This is RB sine 30, which is 1/2. So that is the free body diagram. And of course, you have this 75-pound force. Okay? 75% of the problem. So now you would do what? Summation of moments about the point of intersection of two unknowns. In this case, that point is quite clear. Point A is the only place you have two unknown intersecting. So take summation of moment about that point. What do you have? You have this force that generates a moment that would act this way. So negative 75 times this vertical distance, which is 10. This force, this is the vertical distance from it, and act generates a positive moment, counterclockwise moment. So you have plus 1/2 RB times 12. This force, this is a vertical distance from that point, also generates a positive moment. So you have plus the square root 3 over 2 RB times this distance of 20 equal to 0. You find RB comes out to be 4.2 pounds, and the assumed direction was correct. Any questions? Rest is easy. Summation of forces along x equal to 0. You have AX minus this force, 1/2 of RB, which is 4.2, and that's it. So that gives us AX 2.1 pounds. came out to be positive, that means the assumed direction is correct. Summation of forces along y is equal to 0. You have AY minus 75 pound plus square root 3 over 2 times 2.1 equal to 0. That gives you AY. That comes out to be positive 71.4 pounds. Okay. Any questions?
Would
Well,
it be square root of 3 over 2 times 4.2? Because RB is 4.2.
oh, RB is 4.2. Yes. Why is it 2.1? Yes. Yes. Correct. But that's the correct answer. So I ended up with having more time here. So we can do yet another problem. I could only do 4 problems in the previous section. So I'm sure nobody would complain if I do even one more problem. Okay, that's even better. So I'm going to look at your book, see if there is a good problem, especially I like pulleys. If I see a pulley problem here, would be nice. Okay. Oh, I don't see any pulley problem. I like pulleys. So this book doesn't have good pulley problem. Okay, that's okay. Let's do this problem. All right. So I'm going to do problem 443. That's a good problem. This is the problem. You do have a beam that is supported, fixed end here at point D, and then it is supporting these two loads of 40 pounds each, acting in the middle and the tip. This distance is 4 feet and this is 4 feet. Then at point B, which is 1 foot from here, okay, a cable is attached that goes around a pulley, yet another pulley. So one pulley here and one pulley here, and then is holding a weight of 90 pounds. Okay. So we want, this is some kind of a structure design. Maybe this weight is supposed to counteract the effect of these to keep this straight for whatever reasons. Okay. So we want to find the unknown support reaction forces again. All right. So step 1, set up an X and Y coordinate. Step 2, draw the free body diagram of the structure in the question. This is the structure. So I will cut that from its support. Being a fixed end here, that represents 3 unknowns. 2 unknown forces in X and Y direction and a built-in moment. I assume it is in this direction. I don't know, it may be the opposite, but that's the direction I assume. But what are the acting loads? You have a 40-pound force here. You have another 40-pound here, acting at 4 feet and 4 feet. How about force here? This is a cable that goes around these pulleys, and at the other end of the cable, you have 90-pound load. So the force in the cable, if these two are frictionless, would be the same. So that means, all that means is you have a force of 90 pounds here. If you cut this here, force in this cable would be 90 pounds, and it is acting at 1 foot from here. So this is the free body diagram. Any questions? Let me pause here. If not, let's start with summation of moment equal to 0 at a point where two unknowns intersect and you can get rid of them. And the only possible location here is D. So let's take summation of moments equal to 0. So what do you have? You have an unknown moment in that direction, okay? And then you have moment of these forces. This generates a positive moment, 40 times this distance, 4. This generates a moment, also positive, 40 times 8. This force generates a negative moment of 90 times this distance, which is 5, equal to 0. So this would be 160, or let me factor that out, 40 times 12 minus 450 equal to 0. This is going to come out 480 positive minus that. So you have positive 30. Okay. So MD comes out to be what? 30 pound foot. And the direction that I had assumed is correct. You see, otherwise then the answer would not be a positive answer. Okay, so that means the moment at that location is acting this way. Any questions? All right. If not, let's write the other equation of equilibrium. Summation of forces along x equal to 0. You have dx, there's no other force, is equal to 0. Again, similar to that other problem I did, you may say, why didn't you start with this equation? I could have, because in this special case, that also gives one equation, one unknown. But again, I always like to start with this because that's a general approach. And even this one, summation of forces along y, would be one equation, y unknown, because there is no other unknown acting in this direction. So you have dy minus 40 plus 90 equal to 0. But what happens? dy comes out to be negative 10 pounds. That means the assumed direction for dy was wrong. So dy actually is acting this way. So this should be negative. This comes out to be positive, and this is the answer. dy is acting downward. Okay. Any questions? If not, I will stop here because there's not enough time to start yet another problem. So if you have no other questions, I'll stop here.